All right, for this assignment, I want you to randomly pick a word. So I picked unfinished, and then you're going to select the next 9 words after that. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have 10 words in total. Then you're going to count how many letters are in each word. So my first one has 2, 4, 6, 8, 10, and then 4, and then 5, and 4, and 3. So on my chart, my first word had a length of 10. Is that a short word, which is 3 or fewer letters? No. And then 4, and then 5, and then 4, and then 3. So this would be no, 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 yes. So you're going to do that with all 10 letters. So I'll pause the video, go ahead and do that. Okay, now that you have this filled out, we need to answer question C about quantitative and categorical. Same with D and E and F. And then when you get to F, we are going to put dots up here on the board. So let's say that, oh, my percentages are, well, that's not going to work, whatever. So let's say that 3 of my letters were short. 3 of my words were short. 3 out of 10. Okay, hold on a second. All right, through the magic of video editing, I fixed it. So I need you to answer C, D, and E, and then come up and put a dot wherever your percentage is. All right, this is all the data from the class. So what are the observational units for this sample? What are we looking at? We're looking at words. And what is the variable? And it's, so our variable has to do with the number of letters, but it's actually short word or long word, right? So this histogram is a representation of how many short words were in each class member's sample. Now, is this a very good sample that we did? Is your selection of words truly random? Probably not. My guess is you did not pick a word in the first 3 or 4 lines. You also did not pick a word in the last 3 or 4 lines. Yours was somewhere in the middle. Probably somewhere in the middle of that line, whichever line you chose. Okay? All right, so do a rough recreation of this on your paper. All right. Based on the sample proportions, do you think this sample method is likely to produce representative samples? Probably not. What's wrong with this? Well, first, it wasn't truly random. There's another problem. That right, all 9 succeeding choices were dependent on the first choice. So if we truly wanted to make this random, you could throw darts at it 10 times. You could plug all the numbers, create a list where every word has a number, and then randomly select numbers from that list, which is what we're going to do. Suppose you are blindfolded and pointed to the passage with a pencil 10 times, selecting the closest word each time. Would this method be more likely to produce samples with similar characteristics as the population? Yes. That would be a much better idea, especially if you took the person and spun them around a couple times between each guess. Okay. So let me clear this out. All right, so the way that we are going to make a better sample is we go to Rossmann one chance, and then we go to this random number generator. Okay? And this will generate random lists of numbers. So we only want to do one list. And how many numbers will be in each sample? 10. Right? We're picking 10 random words. So 10. And if we list all of the words from word number 1 to the end, there are 268 words. So this is going to be 268. And with replacement, what does that mean? Do you want to allow duplicate words? And if it's truly random, it would be yes, right? And in this case, it doesn't really matter. Technically, we don't want the same person twice. But as long as your population is large enough, the chance of getting the same person twice is so tiny that we don't even care. Even if you get the same person twice, it's not going to mess things up too badly. So you can choose yes or no. I'm going to say no. And I'm going to sort the results ascending, just because it'll be easier to find the words if we do it that way. So I generate that. Here are 10 random words from the Gettysburg Address. Now, how did the computer do that?
It looked at the time.
It's got some sort of calculator. I don't know what it is, but it's probably looking at what time it is, how long the computer's been on, and then other numerical data, and then it multiplies all those numbers together and uses that to spit out the answer. Some crazy equation. You cannot tell a calculator or a computer, pick a random word. It doesn't know what that means, right? It needs some sort of instruction. So if you said, here are 1 million numbers, pick a random number, there is no command that will do that. You have to generate some sort of number, and then that number will tell you how far to go to pick. And if it's longer than your list, it'll just keep cycling back and starting over. And I don't know what this pseudo random number generator did, but it created that list. If I wanted another list, I could just keep hitting generate. So you're going to do that, and you're going to put down your 10 words, your 10 numbers, and then you're going to look up those 10 numbers and fill out the chart again. How long is it? Is it short, yes or no? When you get that done, I need to put that back up. Then I need you to come up here and get rid of this. Put your dots again. Okay, get to work. All right, so here are the 2 class sets that we did. The green one was the one where you randomly picked, and then we did the next 9 words after that. And then the blue one is the one where we used a computer to generate 10 random numbers. How do those compare? They're kind of similar. 4 was the most common in both. The blue one might be considered a little bit more normal. They're both skewed, I would say, to the right. But the blue one is probably more accurate. Now in this case, is it possible to calculate the parameter? We've done several statistics where we took a sample and calculated the value. Could we do a parameter in this case? Or rather, how would we find the parameter? We just look at the list and count them all. So if I went up here and I counted all the 1, 2, and 3 letter words, that would give me the true value, which is 0.41. So what is that? Where'd my calculator go? So, well, that doesn't make sense. Oh. So yeah, 110. So in the Gettysburg Address, there are 110 short words. Okay. So go into Rossmann One Chance. Go to Exploring Randomness. Where is that? It's not there. Okay, let me find it. Okay, so we're going to go to sampling from a finite population. So this one right here. Click on that, and then it's actually called Gettysburg. Maybe I should change that in the worksheet. I'll do that later. Okay, so once you have selected Gettysburg, you have to click Use Data, and then here is the distribution. How would you describe that distribution? Right skewed. It's got a long right tail. So if you take a sample, what's going to happen? So if you take a sample of 10 words, your sample of 10 words will probably be right skewed. What if lots of people take a sample and we graph all of the samples? That is going to be normal. So this is the population curve, right? If you take a sample, your sample curve should look like that with 10 dots in there, right? So this is the population, this is the sample. If lots of people take samples, we should get a nice normal curve. What is this graph called? Bell curve. That is bell curve, but what's the name of this histogram? Sampling distribution. That's important. The sampling distribution is the graph of many people taking a sample. So, we've done this before, but I think it's valuable. What does that dot there represent? That is one word in the 268 word Gettysburg Address that was chosen at random, right? What is this dot?
Isn't it 10 words?
It's one of your 10 words in your sample. Okay? What is this dot?
It's
One sample of 10 words, and it's the percentage of yeses in that sample. Does everybody get that?
Yeah.
So in the population, this dot is one word from the entire Gettysburg Address. And this particular word had 3 letters in it. Okay? This is our sample. There are 10 dots in this sample. This particular dot is the number of letters in that word from the sample. Okay? And then this dot is one sample of 10 words where we counted the number of yeses and turned it into a percentage, like 40%. Okay? And the population histogram should look like the sample histogram, as long as your sample was done correctly. And the sampling distribution is going to be normal regardless of the shape of these two. So this is a particular number of letters. This is a particular number of letters. This is a sample with a percentage of how many yeses there were in your 10 words that you chose. Okay, does that make sense? All right. Okay, so, and it's not short. Choose variable, short. Okay. And then it says, confirm the population proportion is 0.41. So right there. Check show sampling options, specify 10 in the sample box, and then draw samples. Okay, so where did it say that was? check the show sampling options box.
It's at the top.
Yeah,
Oh, right there. Okay. Make sure it says 10. How many samples do we want to take? Oh, so we can take one sample. So there's one sample. And then we want to take 9,999 more. Draw samples. Okay. What is the name of this curve? Not the shape. What's its name? Not the shape. The sampling distribution. So let's do this again. What does this dot right here represent? One word, which is short among 268 words. Okay. What is this dot?
One word that is short.
One short word out of the 10 words you chose. And what is this dot? One sample of, so that would be 50% yeses. Okay. All right. Okay. So, how do we find the standard deviation of our sampling distribution? So, our parameter, pi, is 0.41. Are we guessing there? No, we know exactly what it is. Why? We counted, well, the computer counted the entire population. Okay, so the standard deviation of the sampling distribution should be the square root of success times failure divided by n. So that's going to be the square root of 0.41 times 0.59 over, not 268. It's not the number of the population. It's not the number of samples. 10. Okay, let's see what that is. And of course my calculator's not on. All right. So, the square root of 0.41 times 0.59 divided by 10 gives me about 0.155, and we can double check that over here. How did we do? Pretty good. Why is it not perfect? Because this is a sampling distribution. This is what happened when we took 10,000 samples. And the sampling distribution is not going to be perfect. Okay. Get rid of this stuff. All right. So now change the population side ratio buttons to select 100 times. Now the population consists of 100 copies of the Gettysburg Address. So here, I click 100, and what that's done is it's copy and pasted the Gettysburg Address 99 times. Okay? Is that going to change the shape of the population histogram? Is this going to change? No, why not?
It's the same proportion.
Do you guys get that? Right? We added more words, but we added the exact same words over and over and over. So if I click this and this, what changed? Just the y-axis, the population size. Okay? All right. So if I go to 100 and I draw the samples, did anything change over here? No. The average is still 0.411 and the SD is still 0.156. Okay? So, what does that mean? Well, it basically means if you want to roll a dice and count the number of times that an odd number shows up, you don't actually have to roll a dice. What else could you do? You could flip a coin. Anything that has a 50% chance of success is going to be identical to rolling a dice and counting the odds. Okay? You change the population, but you didn't change the ratio of the population, so it doesn't matter. So, let's say you had a county and 40% of the people in that county were Republican, and you wanted to do a simulation. You don't actually have to go to the county. You could roll a 10-sided dice and count the numbers 1, 2, 3, and 4. Or you could roll a 5-sided dice, if they exist, and count 1 and 2. All right? But, okay, so has the mean changed noticeably? No. Has the standard deviation changed noticeably? No. So are your answers to these questions what you would have predicted? I'll let you answer that. Okay, but let's go back to 1. What if I change this to 30? What do you think is going to happen? Don't do it yet. Okay, so let's go back. Let's draw samples. Okay, remember these numbers. 0.41 and 0.154. Okay? If I change this to 30, what does that do? What are we actually doing there? What does the 30 mean?
Each dot is 30.
Right, each dot in the sampling distribution is going to be a sample of 30 words. What is that going to change over here? And again, don't do it. Oh.
Make them smaller.
Make what smaller? So let's draw the original samples. Is my suspected average going to be different than 0.41? Or do I expect it to change? So what we're saying is, if you pick 10 words at random, you should get about 41% yeses, 41% small words. If we switch to 30 random words, should we still expect 41% or something different? We should still expect 41%. Because if this is 41%, then this should also be 41%. Okay? So that is not going to change. What about the standard deviation?
Would it get smaller?
Why would it get smaller?
Because it's like squeezing the graph down. I don't know, like you're putting more samples into the one dot.
Not more samples, more.
Sample size.
Samples.
The sample size is bigger, and how is that going to affect the standard deviation?
Make it smaller.
So in general, is a sample size of 10 or a sample size of 30 more accurate? 30. And so if it's more accurate, then the graph should be thinner. And that's going to be visible in this equation here, right? By changing to 30, what did we change inside this? N. And the n is going to be 30, and if I divide by a bigger number, it's going to get smaller. So watch this. The original was 0.15, and now I change this to 30 and do my 10,000 samples, and now my standard deviation has dropped to 8%. Yeah. So by tripling the number in my sample, my graph became about half as wide as it was before. Okay? Does that make sense? All right. All right, so go ahead, answer H, I, and J, and we're done with this.